Hi, my name is Alejandra and I'm going to talk about how we can color our way through Sudoku. But before going into the coloring part, let's first understand what the Sudoku puzzles are. The Sudoku puzzle is just a grid with cells, little squares where the numbers go. A standard Sudoku puzzle has a total of 81 squares, and these squares are sectioned off in groups of 9 to create these 3x3 boxes. And to solve a Sudoku puzzle, each row of 9 squares must contain the numbers 1 through 9, but these numbers can be in any order. Additionally, each column must also contain the numbers 1 through 9, also in any order. And finally, each of the boxes must also contain the numbers 1 through 9 in any order. So the main point of the Sudoku is that no row can repeat any number, because if you are repeating one number, you're also missing one number, right? This also applies to the columns. The columns should not repeat any number, and finally, this also applies to the boxes. They should not repeat any number. In Sudoku, the game starts with some numbers already filled in, and the player must figure out the missing ones. To do this, different strategies can be used, such as cross-hashing or counting, by checking which numbers are already in the same row, column, or box. Normally, many squares will already be filled in, no matter the puzzle level. But as an extra tip, any puzzle that has one single solution will have at least 17 squares already filled in. So, using logic and the process of elimination, we need to deduce which numbers fit in the empty squares. As I mentioned before, to deduce which numbers fit in the empty squares, we can use cross-hashing. That is the process of figuring out where the numbers fit by eliminating possibilities based on the numbers in other squares in the same row, column, or box. For example, in the top middle box, we can observe that there is no number 4, and the other boxes along the top row of boxes do contain the number 4. By the process of elimination, we know that the 4 in the upper middle box must be in the second row, but it cannot be in the middle one because we already have 1 4 in that column. So our only option is this square for the number 4. I also mentioned that the other options is to use the counting method. For this method, what we do is that we look at a single square and count 1 through 9 to all the possibilities, marking off the ones that are immediately disqualified because it already appears either in the same box, the same color, on the same row as the empty square. For example, if we focus on this square, we can observe that in the same column we have the number 1. In the same row we have the 2, in the same column we have the 3, in the same row we have the 4, in the same row we have the 5, in the same column we have the 6, but we don't have a 7. So this is an option. But before jumping into any conclusions, we need to check the rest of the options, right? We can see that we have an 8 in the second box, in the same column and in the same row. And we have a 9 in the same box and in the same row. So our only option is a 7. This is called a naked single, when there is only one possible candidate for a square. There are other strategies. For example, there is one that helps us to find a naked pair. A naked pair is when you have two cells in the same row, column, or block that have the same pair of candidates. But here, we will explore other ways to solve this puzzle using graph theory. This method is nice because it can even solve them when they don't have a single solution, but multiple of them. And this method can find all the possible solutions. For this method, that is a little bit different to the normal method, we need to envision the cells of the Sudoku as vertices in a graph. To represent the connections based on the shared row, columns, and blocks, we use edges to link each vertex to every other vertex in the same row, column, and box. At the end, the graph will look like this. By transforming the Sudoku puzzle into a graph, we can frame it as a vertex coloring problem. In graph coloring, each vertex is assigned a color from a minimal set, ensuring that adjacent vertices connected by an edge have different color. This approach essentially solves the same problem under the same constraints as the Sudoku puzzle, allowing us to gain valuable insights into the combinatorial aspects of the puzzle and providing us a fresh approach to tackle the Sudoku problems. But before seeing all the power of graph coloring, let's first see the basis of what graph coloring is all about. A graph consists of a set of vertices and a set of edges that connect pair of vertices. Let's consider this example of a graph with this set of vertices, 1, 2, 3, and 4, and this set of edges that connect our vertices. If we are trying to color this graph, our goal is to assign colors to the vertices in such a way that no vertex that share an edge share the same color. And to do this, we can employ a recursive function that traverses the graph and assigns the color to the vertices. The function that traverses the graph works by assigning a color to a vertex and then checking whether any of its connected vertices already have the same color. If a conflict is found, it moves to the next available color and repeats the check. Once it finds a color not used by neighboring vertices, it assigns the color to the vertex. This process is repeated for every vertex in the graph. For example, if we start with vertex 1, we select the color, let's say blue, and attempt to assign the blue to vertex 1. But before assigning the color, we need to check if any of the vertices that are connected to node 1 are already blue. If the adjacent vertices have the color, we cannot assign that color, and we need to select a different color from the variable list of colors and repeat the process. But in this example, none of the adjacent vertices to vertex 1 have a color blue, so we can assign blue to this vertex 1. We have colored the vertex 1 with a blue color. Now we need to move to the next vertex. We will move to vertex number 2. To color vertex 2, we select a color from our color list. Let's again take our first option that it's blue. But as vertex 2 is adjacent and connected to vertex 1 that already has the color blue, we cannot assign blue to the vertex 2. So we need to explore alternative colors from our color list. And in this case, we are going to say that our second color is red. None of the adjacent vertices to vertex 2 is red, so we can assign red to vertex 2. Now we have colored vertex 1 and vertex 2, with the colors blue and red respectively. We need to move to the next vertex, the vertex 3. To color vertex 3, we select our first color, that it's blue. But we can observe that vertex 3 is connected to vertex 1, that already has the color blue. So we need to jump to the next color, that is red. And because none of the adjacent vertices have the color red, we can assign red to vertex 3. Continuing to vertex 4, we again start with our first color, that is blue. But because vertex 1 is already colored with blue, we cannot assign blue to 4. So we proceed to check the next available color, that is red. But because vertex 2 and 3 are already colored with red, we cannot assign red to vertex 4. Then, we need to proceed to the next color, which is going to be green. Now we check all the adjacency vertices again to verify that none of them are already colored with green. Because this is not the case, and none of them are colored with green, we can assign green to vertex 4. And we can see that the entire graph can be colored with 3 colors, blue, red, and green. As we saw, the recursive function traverses the graph, selecting a color for every vertex and checking its compatibility with the adjacent nodes on each step. If a color is found to satisfy the adjacency constraint for a particular node, it is assigned to that node, and this process continues until all nodes in the graph are assigned colors. Luckily for us, we don't need to program any of this, because Wolfram language already has a function that finds the optimal vertex coloring. This function can be used to automate the process of assigning colors of the vertices of a graph, ensuring that not two adjacent nodes share the same color. Now that we know what's graph coloring, let's get back to our problem. The last thing that we need to solve the Sudoku puzzle is to include the hints into the graph structure. To understand how to integrate the hints into the Sudoku graph, let's consider the following Sudoku puzzle. We are going to focus onto the sevens to see how we are going to be including the hints into the graph. The first thing that we need to do is that we need to ensure that the number 7 is not present in the row, column, or block where it already exists. But we also need to enforce that the two vertices representing the number 7 have the same color. To achieve this, we introduce additional connections between the two vertices with the number 7 in the Sudoku. This connection is established by connecting one of the vertices. This connection is established by connecting one of the vertices with a 7 with all the neighbors of the other 7. What I mean with this is that we connect all the neighbors of this 7 with this 7. Of course, skipping connecting the two 7s. We do the same for the other 7. We connect all the neighbors of this 7 with this 7. And this way, we are already forcing the two 7s to have the same color. We also need to introduce additional connections between the vertices with the number 7 and all the vertices that have a different number than 7. How are we going to do this? We're going to take all the 7s and all the other numbers that are not 7, and we are going to connect them. We are going to do the same for the other 7. We connect the 7 with all the other numbers that are not 7. Integrating these hints of a given number in the Sudoku graphs involves adding these additional connections while maintaining the original connections based on row, columns, and blocks. This process creates a more interconnected structure that captures the relationship between a given number and their constraints. We can implement this integration of the hints with the following functions. And with this, we can find a solution for the Sudoku puzzle using graph coloring. What this function is doing is that it takes a puzzle as an input, which is a matrix representing the Sudoku puzzle, and it brings the solution. But we can also visualize the solution with the following function. What is happening is that by representing a Sudoku as a graph and using graph coloring algorithms, we are assigning a number to the cell, respecting all the constraints and obtaining a valid solution for the puzzle. It's important to note that this approach can work for any valid solution problem, regardless of the number of solutions. So even if a Sudoku has multiple solutions or an infinite number of solutions, the graph coloring algorithm will still find a suitable correct solution, ensuring that no adjacent cells have the same color. Graph coloring can also be used to determine whether a Sudoku puzzle has a valid solution. This is achieved by examining the vertex chromatic number that represent the number of colors needed to color a graph so that no two adjacent vertices share the same color. For a Sudoku puzzle, if the chromatic number exceeds 9, it indicates that there is not a valid solution. And conversely, if the chromatic number is exactly 9, we can guarantee that there will be a solution. For example, if we take this puzzle that we know for sure that doesn't have an answer, we will find that the vertex chromatic number is 10. So with this, we can create a function that checks if a Sudoku puzzle has a solution or not. In this case, we can check that this puzzle doesn't have a solution. So graph coloring can be used to determine whether a Sudoku puzzle has a valid solution. At the end, graph theory and graph coloring techniques can be applied to solve the Sudoku puzzles, maintaining constraints and systematically finding a valid solution for the Sudoku puzzle. Sudoku's puzzle also have a magical property called the fist-to-method ring, property that exists in all Sudokus, and I think it's quite lovely because it says that the digits in the red ring are exactly the same digits as the green corners. And you can try to do this in any Sudoku puzzle, and it will work every single time. It's also magical that we can observe this in the graph form. One way to observe this is by taking our Sudoku graph, extracting the subgraph that we are interested in, and finding the coloring. And we can observe how the colors repeat the exact amount of times. For example, if we have 4 greens inside the ring, we will have 4 greens in the 4 square corners. We can even observe how the colors repeat exactly the same amount of time. At the end, we have explored how graph theory and graph coloring techniques can be applied to solve Sudoku puzzles, how by representing the Sudoku as a graph and using graph coloring algorithms, we can assign numbers to find the solution, respect all the constraints, and obtain a valid solution for the puzzle. But graph theory and graph coloring go beyond and have broad application beyond Sudoku. It can be applied to other combinational problems and optimizational challenges, and it's quite lovely how graph theory techniques offer valuable tools for solving Sudoku and addressing real-world problems in a structured and a systematic manner. Thank you very much for your attention. Any questions, comments, or suggestions that you may have are more than welcome. If you're interested in this kind of problems, follow our YouTube channel, Wolfram R&D. I also encourage you to join us for a facultative session or Q&A. And if you have any ideas or projects in mind that involve graph theory, please don't hesitate to reach out. I will be delighted to hear about them and, if possible, contribute to the development. That was very quick, so we have a lot of time for questions. I see one question that is if there is a Sudoku resource function, and there is some in the function repository. And yeah, it's like 2 or 3 functions for Sudoku to check if the Sudoku has a solution, to find the solution, and they are up. There is also one to find the graph of the Sudokus, and there's another question if I have looked into the real world application to apply this to. I actually did not, but we published one community post on this. And there was one person that works with Sudoku puzzles, and he tried this algorithm and compared to the other algorithms that are like very used to solve Sudokus. One of the comments that he told us is that it is a very, very fast algorithm, and that it was beating other algorithms on time, especially for very complicated, non-trivial Sudoku puzzles, the kind of that have like lots of multiple solutions, multiple options of solutions. So I think that's one of the real applications that we have. And we have another question. What was the Wolfram channel that you mentioned? It is Wolfram R and D. I think, let me see if I can share the screen. Here it is. We're also working on more videos. This one. This is the and we're also working on more videos. We are especially working on one that it's ready. It's the analysis of the Mexico City subway network with graph theory. We do the full analysis, and the video it's almost ready. Like we just need to publish it. There is another question, for example, if we have tried to use some application for town planning, that would be actually very interesting. I think it will be some of the other parts, but because we try to keep it like simple, we have not done yet, but that will be very interesting. There's another question. If the computational time depends on the Sudoku size, it does. One of the, well, not problems, but one of the things that happens is the bigger they are, the graph, it's going to get bigger. So it's going to have more connections. And for this, there is like some limits of how big it can be. I mean, we're never going to reach the 10,000 by 10,000 Sudoku, but yeah, it does get increasingly complicated, but it is it's still way more fast than other algorithms for Sudoku puzzles. Thank you for the comments. And yeah, well, if there is no more question, I can keep giving more advertising. Well, at the end, I think like the graph theory is very, very useful. I feel like it has applications everywhere. And for example, we have also used it for the solution of the N-Queens puzzles. We have, as I mentioned, used it for the analysis of the Mexico City subway network. And right now we are working on the exploration of how to find the fastest solution for the Rubik's Cube. Yeah, I feel like graph theory is the perfect tool for this kind of task, to find the faster solution and use it in a new approach. And yeah, so I recommend you to go to our YouTube channel. Stay tuned because we will be posting some nice things there. And well, also the Wolfram language is like the perfect tool to do these explorations, because all the algorithms are already implemented. You don't need to try to think like, oh, how I'm gonna do the algorithm for graph coloring. You just apply the algorithm that is already implemented, so you don't need to be like overthinking that part of the code. You just go directly to the real application, not to the details and so you don't get stuck in the part that is not that interesting. That it is interesting, but it is not as fun as just apply all this functionality. But and if there is no more question, I think we can close the session. And I got one more. Can a method be used to generate puzzles? Yeah, it can actually be used for generate any puzzles. Actually, that would be like the first thing, because just by having the puzzle graph, we apply the coloring algorithm. without including any of the clues, and it would automatically generate some of the puzzles, no? And then after you generate the puzzle color, you can just decide which hints to delete. So that was actually the first part that we did. It's just after generation of the graph, you can just color it, and that will be one puzzle after deleting some of the entries. Well, thank you so much for your attention. We also have a Q&A at 1 p.m. for the discrete computation. So if you want to have more questions, if you are having troubles with anything, just jump in and we will try to help you. Well, thank you so much. I hope you continue enjoying the technology conference, and thank you.